Okay, welcome to lecture 3.6. You know what, in 3.5, I told you I was going to look at an identification problem. I changed my mind in the meantime. I think I'll do that in 3.7. I want to take a moment first, and before I do that identification problem, I want to explain why the likelihood function I wrote is not quite the likelihood function that Levitt and Porter wrote. And I want to explain why our two likelihood functions will get you the same parameters. Well, but I want to just explain why they look different. Okay, review. Here's what we got our likelihood function. Here's for a case. So I had 5 observations. This would be the likelihood function of those 5 observations. Okay, I put ... at the end there because supposedly it's more. Maybe it's 10,000 observations, and those are the first 5. Okay, a couple definitions. Okay. Well, first, you know what? Let me show you something. Here's where we're going. So notice that PDD appears twice in this. So we could have written this PDD squared, and then we'll also notice PSD appears twice. We could have written PDD squared times PSD squared times PSS. We could have written that, okay? The key is notice that we had PDD raised to the 2 power because there were 2 observations where the dependent variable was 2. That is, there were 2 drunk drivers. Then there were 2 observations where there was exactly 1 drunk driver, and then exactly 1 observation where there was 0 drunk drivers. Okay, keep that in mind. All right. Levitt and Portman define A sub D equals number of cases in which both drivers were drunk. You know what? Instead of both, I'm going to say two drivers were drunk. Okay. So remember, that's their data. They had all these cases where, and they divided it up into different time periods. So suppose we were just looking at one time period, say Friday nights from midnight to 1 a.m. Okay. So Levitt and Porter, they would look at all their data, all the fatal crashes, look to see involving 2 drivers, but they threw it out there as a 3-car crash. Or 1-car crash. They would throw it out of their data set. So they would just look in those, and it was available how many of the drivers were drunk. So if it was 2, they would put ADD equals that many, however many were 2. What did they do? DS, is that right? Did I use... I never remember if I used DS or SD. Okay, DS. DS equals number of cases, number of accidents in which exactly 1 driver was drunk, and then ASS equals number of drivers in which 0 drivers were drunk. Okay, so we have that. Okay, now what that means, let me go back to our likelihood function. Okay. You know what? I think I'm going to rewrite it. Okay. Let's see if I can memorize this. DD, SD, SD, SS, DD. Okay. So, L. You know, I'm going to write our parameters again. I want you to remember this. ND ns theta d theta s. And the key thing, I'm writing this again. Notice, typically when we write a theta likelihood function, we write it as a function of the parameters. And note this, the AD and AS's are not among these arguments. These things are data. These are given. We're not varying those to maximize the likelihood function. We're varying these things, okay? So this, for our little example, it was, well, we know we can rewrite it as P dd to the A dd, okay? So in the old case, we had two cases where there was two drunk drivers, so that would be a 2, and times P ds raised to the A ds power, and that was 2 in the old case, and then times P ss to the A sub ss. Okay, and that was 1 in the old case. Okay. All right, now that is what I'm using as the likelihood function. Okay. Okay. So this is Tim's likelihood. So Levitt Porter, though, had L equals, okay, now, did I write it down? Okay. It was exactly this thing plus some stuff, or times some stuff. It was ADD plus ADS plus ASS, parentheses, factorial divided by ADD factorial. Let me get this right. ADS factorial ASS factorial times the same stuff. P. You don't want to put this term in brackets. PDD to the ADD times PDS to the ADS times PSS to the ASS. All right. The key thing I want you to notice, remember, as I told you, these A terms are just data, okay? We're not varying those to maximize L, okay? So for all intents and purposes, for our purposes, which is to pick ND and S, theta D, theta S to maximize L, this term in brackets is just a constant, okay? We can't change the value of that by varying those ND, NS, and so on, okay? So what we have is Tim's likelihood function. The difference between Tim's likelihood function and Levitt and Porter is just a constant, okay? So if we find the NS, ND, and theta S that maximizes this, it's also necessarily going to maximize this thing, okay? So that's why it doesn't matter if you put, that's why Levitt and Porter put in this term. It doesn't matter if you take it out, okay? As long as it's not 0, okay? I think it's got to be positive, maybe. As long as it's not infinity, okay? But if it's a constant between, some finite constant, you can just remove it. And you will get, when you maximize the likelihood, you will get the same estimates of ND, NS, theta D, and theta S, okay? Here's the intuition. And by the way, where'd they get this constant? Okay, well, let me back up, okay? So remember, in the earlier example, I had the likelihood, and what did I have? I had equal PDD times PSD times PSD times PSS times PDS DD. Okay. So I had the observations ordered. Suppose those were the actual order that they came chronologically. You know, the observation 1 was the first crash in our data set, observation 2, so on. Okay. So I ordered it. The first observation had 2 drunk drivers. The second one had 1 drunk driver, 1 sober driver. Same thing with the third, and so on. Okay. The likelihood function is exactly the same if we reorder these things. So instead, if we call that the first observation, PSD, that one the second, PDD, and make that, call that one the third, PSD, and then keep that one the fourth, keep that one the fourth, PSS, PDD. So what's that? Did I write that? PSS, PSS. By the, I think it's the commutative property. It's one of those properties I think you learn in 6th grade. Whatever, maybe it's associative. I think it's commutative. By the commutative property, that's got to equal that. Okay, so it doesn't matter how we order the observations. The likelihood function's not going to change. Okay, and the same values that maximize the first one are going to maximize the second one. Okay, so the idea is that whatever order the observations came in chronologically, we can change them around and it won't matter. Okay? So that's under my likelihood function. Now, not only that, and not only that, once we had it, all that really mattered was, in the end, we just grouped these together. We grouped all the PDDs together and put an exponent of ADD. So all that mattered was the number of observations that was drunk, the number of observations that was drunk, sober, and so on. Okay, so doesn't matter the order. We could reorder those observations however we want. We get the same thing. Okay, not only that, suppose that we're just agnostic on the order, that we just throw out the order. Okay, we don't even say it. We just say, look, all we care about is the number of cases in which there were 2 drunk drivers, number of cases there was 1 drunk driver, number of cases there were 0 drunk drivers. Okay, that is what Levitt and Porter do. They say, we're not even going to record the order nor impose any kind of artificial order on the observations. We're just going to say we know the number in which it's drunk, number in which it's drunk, sober, number in which it's sober. Okay. And they said, well, once we do that, suppose we have 20 drunk, 10 drunk, sober, 5 sober. And they say, well, what's the probability, given that there were a total of, 20 plus 10 plus 5, 35 observations, what's the probability of observing exactly 20 drunk, 10 drunk, sober, 5 sober. And then it's just a combinatorial problem, hopefully from your freshman or sophomore probability class, and it's just this problem. It's the probability that the observation is drunk, raised to the power how many, and then times, same thing, probability that's drunk, sober, raised to the number you have the drunk, sober, probability sober, raised to the number of sober, and then times the number of different ways of choosing 10. It's like the marble problem. It's like you have red, green, and white marbles. You know, you have 35 total marbles. What's in your sample? What's the probability of getting 10 of them green, 20 of them red, 5 of them white? And it's this this term in brackets times those probability terms. Okay, so that's what Levitt and Porter do. They say we don't worry about the order. We just say we got the number. Mine I'd say let's impose an order. Maybe it's artificial, okay? But once we do that, just say we actually had the chronological order, then it's exactly the same as what I've given. And hopefully you see I'm kind of waving my hands a little bit why what Levitt and Porter, how they describe the problem and how I describe the problem really doesn't matter in terms of what our optimal parameter estimates are going to be. And and hopefully you can see that why it's the same reason why all it does is just multiply it by this constant. Okay, but the key is, okay, I'm trying to give a verbal way of describing it. Doesn't matter what you do. Okay, use my way or the Levitt Porter way. Now I think my way is a little simpler. Okay, and I would suggest for your homework you do it my way. There's going to be fewer terms you got to plug in into your Excel spreadsheet. Probably going to have fewer chances that you're going to write in a typo. So I'd suggest you do it my way. Okay, so that quickly, maybe it wasn't so quick. 16 minutes was the reason why. For my lecture, the likelihood function looks a little bit different from what Levitt and Porter describe in their paper. Okay, so that was, I think, 3.6. Was that 3.6? Okay, and I will see you in lecture 3.7.